Today we're talking about applications of differentiation, the second part, the analytical perspective. And today's visual aid is going to be about optimization. So right here we have a rectangle drawn between the x-axis and our parabola here. And the question is, can we find the rectangle out of all of these that has the maximum area from a calculus point of view without just guessing and checking and guessing and checking? Because we have the area put down here. So as we go, we could try to find it just by guesswork, but we know there is an easier way, and that involves optimization. So first, things you need to know: critical points, and that's going to include relative minimums and relative maximums, and absolute minimums and absolute maximums, and we'll talk about those. But there any point where there's a discontinuity, a horizontal tangent, or a sharp corner in any function. And then global extrema are all the critical points in a function. So that's going to be your absolute maximums and your absolute minimum points in the function. And then relative extrema are going to be all the critical points and endpoints during in one interval. And that's going to include your relative minimums and your relative maximums. And the reason we say that is just because if you have a function that starts and ends, say you have a linear function, and it starts at 0 and it ends at 5, your maximum point is going to be the end point at 5, and the minimum point is going to be the point at 0. However, those aren't really critical values over the whole function. There aren't really maximums and minimums over the whole function, just over that interval. And then the last thing, the extreme value theorem. If a function is continuous over a given interval, it has a minimum and a maximum value guaranteed over that interval, and that may be the end point and the start point, like we're talking about. All of these are pretty intuitive once you get talking about them in context. You just have to know the terms. Sometimes in your AP FRQs, they're going to get you a couple points if you can say, hey, this is a global extrema, this is a critical point, this is a relative min, this is a global min. But just practice and you'll get the terms making more sense. And now this is our problem today. It has to do with optimization. So we say we have this flat square of paper, and we're going to take out an equal size square from each corner of length x and width x. It's a square. And then after we take out those squares, we're going to fold the box along these dotted lines. Fold all of these four like tabs up. And we're going to make a sort of like box with no lid. If you can imagine, this square in the center is the base, and then all of these are the four sides that we're going to fold up. And the question is, at what x value are we going to have the highest volume box? And just keep in mind for later in this point, if we have an x greater than 5, we can't have that because we only have 10 centimeters. And if we were to cut off a whole 5-inch box from each four corners, we're going to be cutting the entire box, if you can kind of visually see that. We also cannot have a negative x because we cannot be cutting outside the box. So our x has to be less than 5 and greater than 0, but that won't come into play until the end of the problem. Now the steps-wise way to solve an optimization problem is sort of similar to our related rates. We're going to find a function. We're going to take the derivative of that function. We're going to find our this is where it gets different. We're going to find our critical values, and then we're going to substitute in those critical values to find the highest amount, because all of our critical values where the derivative equals 0 or where the derivative doesn't exist is going to be our maximum and minimum values, and that's what we're looking for, is the maximum area. So in this case, we're looking for volume, so the equation we're going to find is going to be our volume equation for the square we're making. And we now, for any rectangular or square prism, we're going to be using base times width times height, length times width times height. And in this case, our width is going to be, for our box, our width is going to be this length right here. And that is the whole 10 centimeters minus this segment, which has length x, like we said here, minus this segment, which has length x. So our whole thing is going to be our 10 centimeters minus x minus x. We're going to write minus 2x. That visually makes sense. It's 10 centimeters minus x minus 2x, and that's this value, this length right here. Similarly, the length, or the other side of the base, is going to be this, which is also 10 centimeters. This length is also x. This length is also x. So we'll have another 10 minus 2x. So instead of writing it again, I'm just going to say 10 minus 2x squared, because we know we have 10 minus 2x times 10 minus 2x. Then our last volume, our last measurement is going to be our height. And now if this would be a side of the box, all four of these are sides of the box once we fold them up. And that means this is going to be the height of the box. This too, all of these are going to be the height of the box, which we've already established. This is the same as this, which is x. So now we have a full formula. Volume equals 10 minus 2x squared times x. First thing we're going to do, because we need to take the derivative, I would rather take a simplified derivative than have to take the derivative of something complicated like this. So I'll rewrite it as volume equals a squared plus 2ab plus b squared, just to get rid of this squared parenthesis right here. So we have 100, this is a squared, minus 40x plus 4x squared. This is still multiplied by an x at the end. And now we don't have this squared anymore. Next step is going to be to distribute out the x. So now we have 100x minus 40x squared plus 4x cubed. This is our finalized volume formula. And now to find the extreme values in our volume formula, we're going to take the derivative. This is where it gets more simple than related rates, because we don't need to take the derivative with relation to anything else. We can take it with relation to x, which is going to make it a little easier. We can just use our normal power rule, and we don't have to worry about those extra d whatever dx. So we'll have 100, this is all power rule, minus 80x plus 12x squared. This is our derivative. And now we can already see, if you know your essential parabola function, this is just a normal parabola. There's going to be no sharp corners, there's going to be no discontinuities, jumps, anything like that. So we can go straight to looking for values where the derivative equals 0. And right away I see 100, 80, and 12 are all multiples of 4. So just to make this a little easier to look at, I'm going to divide everything by 4. 25 minus 20x plus 3x squared. Final step, second and final step, is to look for our values where x equals 0. Now first I would look if you can just factor this out. Unfortunately, this is not factorable into clean whole numbers. So if they give you a problem like this on the AP test, I would use your calculator. There's a app where you can find the roots of a polynomial expression, or you could just graph it. I'm going to just graph it here. So our derivative formula is 3x squared minus 20x plus 25 after we simplified it. Now we're looking at our root. So we have 1 at 1.667 and 1 at 5. And we already said, this is where it comes back, we already said earlier if we were to take out a segment that is 5, this whole thing is 10 centimeters long. If we were to take out a segment that's 5 centimeters long, we would end up taking out the entire thing, which is not feasible. All 4, we would end up cutting it. We wouldn't be able to fold it up. So we cannot use this 5, so we have to use this 1.667. Also going to put in our original function, which was 4x cubed minus 40x squared plus 100x. And now we have a sort of complicated function. You can see we can disregard all the values above 5. It starts going up after that, but we can't use those values. So if we zoom out, our value of 1.667 happens to be our maximum value with our maximum area. This blue line, the y value, represents the area. This is the maximum feasible area of 74.074. And that's how you would solve a problem like that.